Watch the continuous motion of a vibrating membrane. As kinetic energy travels outward from the center, the surface ripples in overlapping physical waves. Mapping that motion requires this multivariable partial differential equation. It is a dense expression of multivariable calculus. This equation is a macroscopic expression of Newton's second law: force equals mass times acceleration. To prove that, we have to look past the macroscopic behavior of the drumhead and deconstruct the physics down to its microscopic foundations. We start by establishing a geometric space, a perfectly flat, uniform two-dimensional plane. This grid represents our elastic membrane, resting in pure equilibrium before any external forces are applied. Understanding the dynamics of a continuous wave requires us to first define the rules governing this static system. We define our primary variable, u of x, y, t, as the vertical displacement from its resting point. Next, the material is pulled by a uniform tension, T. Our second constant is ρ, the mass per unit area. Finally, we enforce our geometric boundaries. The membrane is perfectly flexible, with zero bending stiffness, and motion is strictly vertical. These idealized assumptions are the constraints that allow us to calculate the system's behavior using linear mathematics. We dive into the surface of the membrane until we can isolate a single microscopic rectangular section from the rest of the material. This specific element has a width of delta x and a depth of delta y. To find the net vertical force acting on this single patch, we analyze the tension pulling at its four edges. We will focus exclusively on the two opposing edges facing the x direction. Internal tension always pulls tangent to the membrane surface. When it displaces vertically, that tangent pull tilts, creating a vertical force component. Geometrically, the vertical force on this edge is tension times the edge length, delta y, times the sine of the slope angle, theta. The sine theta term represents the steepness of the membrane's slope at the boundary line. This tension force happens simultaneously on the opposite edge, pulling in the other direction. To determine if this patch moves, we measure the difference between the angles of these two opposing edges. Because the physical displacements are microscopic, we can apply the small angle approximation, where sine theta is virtually identical to tan theta. In calculus, tan theta is the definition of slope, written as the first partial derivative, du by dx. The total vertical force pushing on the patch is the difference in this slope from the left edge to the right edge. If the slope on the left matches the slope on the right, the upward and downward vertical pulls cancel exactly. A straight, unbending slope yields no net vertical movement, regardless of how steep the angle is. For a net vertical force to exist, the slope must change across the distance of the patch. This change in slope across a surface physically requires the membrane to curve. The rate at which the slope changes is the spatial second derivative, partial squared u by partial x squared. To find the total change over our specific patch, we multiply this second derivative by the width, delta x. This gives us the x direction force, tension times the edge length times the change in slope. A spatial second derivative is the physical measurement of curvature that generates a restoring force. We now return to the three-dimensional patch to look at the remaining two edges facing the y direction. Applying the same logic, vertical force from these edges relies on curvature along the y-axis. We substitute the y-axis second derivative to find the y-direction force component, then combine the x and y components to define the total vertical force, F, acting on the patch. We can now address the mass times acceleration side of Newton's equation, starting with the mass of our rectangular element. Mass is the material's surface density, ρ, multiplied by the geometric area, delta x times delta y. The patch's acceleration is the second temporal derivative, delta squared u over delta t squared, which measures how vertical displacement changes over time. Setting the total force equal to the mass times acceleration establishes the complete mechanical equation for this microscopic patch. This equation connects localized, discrete Newtonian mechanics to the continuous geometry of waves. The newly assembled equation contains a redundancy, the geometric footprint of the patch. Because the area exists on both sides of the equation, we can divide it out completely. This leaves the physical constants, tension on the left and surface density on the right. Dividing both sides by the density isolates the temporal acceleration term. By dividing out the arbitrary geometric dimensions of the patch, we arrive at a continuous partial differential equation. The localized rules governing an infinitesimal speck scale to dictate the behavior of the entire system, regardless of the size of the patch you choose to measure. We focus now on the ratio that remains in our simplified equation, tension divided by mass density. We group this ratio into a single constant, c squared, finalizing the 2D wave equation. This constant c defines the exact speed at which waves travel across the membrane. A higher internal tension creates a much more violent restoring force, which propagates energy faster across the entire surface. Conversely, a higher surface density increases the inertial resistance, making the material sluggish and visibly slowing the wave down. This describes the physical difference between the sharp, fast strike of a tight snare drum and the heavy rumble of a bass drum. The multivariable notation is a mathematical translation of microscopic tension fighting against microscopic mass.